Let's first introduce nonlinear and complementary two ports. And basically, it is exactly the same uh, concept as we did with two terminal elements. But now we have, as you know, we have 6 possible notations for nonlinear two ports. I also put an extra line in it to stress the direction of the nonlinearity in the device. That is very important. Otherwise, we don't know what anti-connection is or normal series connection. No, this is like you could have done it with the plus minus signs inside as well, so you can leave it out. But I just gave it an extra line to stress out how is the orientation of the non-linearity of the device. So we have 6 kind of notations for such a device. And we use the anti-causal notation in which we write the input voltage and the input current as a function of the output quantities. So that will be, of course, different functions, and there will be general, in this case, nonlinear functions. So a complementary device, we write it in a similar way, but now with G instead of F. And we call the functions complementary. So we call the two ports complementary if G operating on VOIO is the same as minus F G operating at minus VO and minus IO. So that is for both functions G1 and G2, of course, related to their correspondent F function. So this is the definition of a complementary two-port, and this is this is the way you could derive equations for a N device and from a P device, or the other way around. And this is basically how SPICE does it. So let's go to we cannot always have complementary devices. Now, in semiconductor technology, we have PNP transistors and NPN transistors, and CMOS, we have N-channel MOSFET, and we have P MOSFET, but we didn't have with radio tubes. We had only N devices. We didn't have P radio tubes because we just needed the electrons to leave the cathode, and we cannot put holes in vacuum. So there we needed another way of constructing complementary elements. And here is a way of doing it. I will show 3, but there's 1/4 as well. That I didn't place here on the picture, but I will tell you later. So what you basically do is you switch the sign with respect to the nonlinearity of it. So the sign of the signal is going to be the other direction as your orientation of the nonlinearity compared to the normal device. So if the upper device on the left is my normal device, then now on the right, I have made a swap at the input and a swap at the output of the signal with respect to the nonlinear VI curves at the input and at the output. So at one place, I have swapped it with a transformer, which creates also isolation. And at the other point, I just left it by swapping the terminals. Of course, you can do this also by doing it at the other node. And you could also use 2 transformers. But you can also use no transformer at all. You can swap both the input and the output. And that's the one that is missing here in the picture. Just the direction of the signal, you have to swap with the direction of the nonlinearity. That is basically what we did by reversing, placing the element the other way around in the anti-series connection with the with the 2 terminal element. So that's exactly the same mechanism. So let's look at possible interconnections that we can make then. So here we have 2 identical 2 ports, identical nonlinear 2 ports, and we place them what we call anti-series. So plus, minus, minus, plus, or the orientation of the nonlinearity is the other way around, which makes, of course, the signal having the other orientation with respect to the nonlinearity in both devices. And that is the whole trick. That's what you are doing, basically. So complementary series, then we have a complementary device. So you place them normally in series. We can put them anti-series at the input and anti-parallel at the output. We can put them complementary series at the input and complementary parallel at the output. Let's say if we have a complementary device, we have complementary both for the input but for at both ports. Yes, so you cannot do one series and one complementary. That solution doesn't exist. So we have anti-parallel in and anti-series out. We have, and same for complementary, then anti-parallel in, anti-parallel out, and here complementary parallel in, parallel out. Let's now think about something, looking at this picture and thinking about our transistors. So a transistor, a CS stage, is basically a three-terminal element. So I can imagine if you put if the input is the gate and the output is the drain and the common terminal is a source, that the upper one, the anti-series, so left upper, that works with transistors. I can put there a CS stage in, and that is a valid solution. But if I would do it with a complementary thing, so then it cannot be done, because then it will be short. If the minus in the complementary will be the drain, the source. So the plus is the gate and the other one is the drain. So here, if I look to this, the complementary series, I would take the normal device as N and the other device as P, the complementary device. Then the minus will be shorted, both, but also then the input, the plus of the complementary device with the plus output of the complementary device, because that goes to the minus of the N device. So the complementary series is not possible with three terminal elements. And also the anti-series, so the only one that is possible, we go to the end, completely at the end. There you see I have minus again connected to each other. So at the end, the complementary parallel in and the complementary parallel out. There I can also put one transistor in, and one would be then an M device and the other would then be a P device, and that will be a valid solution. So if I go from all these interconnections to what I could make with a single transistor as let's say element that represented by such a block, then only the anti-series and the complementary parallel holds. And for all the others, I will have what we call a port conflict, and such a port conflict, of course, can be resolved by placing transformers in between, because that's how we can create maybe isolation.